Hi everyone, let's continue with 8.2. Okay, so last time we talked about sequence and let's continue to compute the limits of the sequence. Okay, so here we have the limits. Oops, let me use black color. Okay, so we have the limits. N goes to infinity of a sub n is the limits, and goes to infinity n cube. You can see e to the minus n. That means we have e to the n in the denominator. Okay, so last time we talked about sequence is just like a special case of function. Okay, so do you remember how can we find the derivative of n cubed over e to the n? Well, what happened when n goes to infinity? Well, you can see the numerator will go to infinity. The denominator, e to the infinity, is also infinity. Okay? So when we have infinity over infinity, we use what? L'Hopital's rule. Okay? So when we use L'Hopital's rule when we see 0 over 0 or infinity over infinity. Okay? So what's L'Hopital's rule? Okay, L'Hopital's rule tells us that this limit equals to, we take the derivative of the numerator over the derivative of the denominator. Okay, so derivative of n cubed is 3n squared. So we think about n is like the variable. And then derivative of e to the n is e to the n. Okay, so here when n goes to infinity, we still have 0 over 0, so we use L'Hopital's rule again. So at the step when you use L'Hopital's rule, please make sure you write the case infinity over infinity, or is like 0 over 0, and make sure you write L'Hopital's rule. Okay, so that equals to limit n goes to infinity, the derivative of 3n squared over e to the n derivative. Okay. The derivative of 3n squared is 6n. Derivative of e to the n is e to the n. You can see when we differentiate the polynomial, the degree is smaller until we reach the constant. But the exponential function is always the same. So here we still have infinity over infinity. We still use L'Hopital's rule. So we will get 6n prime over e to the x prime. Almost there. Okay. So we have 6n prime is 6 over e to the n. Now you can see we have constant over infinity, and that is 0. So 0 is our limit. Okay? And if you can remember that exponential functions grow faster than all the polynomial. Okay? So let me write it down. So exponential function grow faster than polynomial. Okay, how about the logarithmic function? If you can remember, the logarithmic function grows slower than the polynomial. Okay, why is that? I can show you an example. If we have like n goes to infinity of ln of n over like n squared, something like that. Okay, so we have infinity over infinity, and you can use L'Hopital's rule, is ln of n prime over n squared prime. And ln of n prime is 1 over n squared prime is 2n. So you get, this is 1 over n over 2n is the same as 1 over n times 2n. Why is that? Okay, so I'm trying to write all the formula we use. So why is that? That is because a over b over c over d is what? Is a over b times d over c. Okay? So that's why this is like a, 1 is a, n is b, 2n is like c. So you put 2n actually in the denominator. Okay? Alright. So this is the limit n goes to infinity of 1 over 2n squared. We have constant over something goes to infinity is 0. 0 means what? You have numerator and denominator, and then the limit is 0. It means which one grow faster? The numerator grow faster or the denominator grow faster? Yes, the denominator, because your denominator is bigger, and then your number is smaller. So it means that the denominator and square grow faster than the logarithmic function. Okay, in the previous example, we can see the limit is also 0, so the denominator, which is the exponential function, grow faster. So if we want to use a notation, we can say, let me use a fancy notation. Gotta see. We can say the logarithmic function, okay, grows slower than the polynomials, okay, and grows slower than the exponential function. Okay? Alright, so let's continue. So part D, you can see it's very similar to part A, but the difference is there is a -1 to the n factor, okay? But you can remember that in this case, we can compute ln of absolute value of a sub n. And then this is going to be the -1 to the n become 1. So we have n cubed e to the minus n. Well, that's exactly part C, right? From part C, we get 0. And then from our theorem. So last time we talked about the theorem. What is the theorem? The theorem tells us that ln of absolute value of a sub n is 0 if and only if the limits of a sub n is 0. Okay, so the limits of absolute value of a sub n is 0 if and only if the limits of a sub n is 0. Okay, so let's go back to our example. So because ln of a sub n is 0, so by the theorem, we get, so limits of the sequence is also 0 by that theorem. And we get the sequence converges. Okay, if we get a number, then sequence converges. Oh, did we say that in the last example? Okay. Yes, so, in part A, we forgot to say that. So the limit is a finite number, so the sequence that converges. Okay. In part B, we say the sequence diverges. And part C, so the sequence also converges. Part D, the sequence converges. Okay, so let's look at part E. Well, when you see sine function there, think about what? Squeeze theorem, because sine is bounded between -1 and 1. So how do we get sine of 2n into our function? We add 1 on each of the terms. So when we add 1, -1 add 1 is 0. And then we have 1 plus sine 2n. And then 1 plus 1 is 2, okay? And then what do we do next? We divide it by square roots of 1 plus n. Because square roots of 1 plus n is positive, so it won't change the inequality. And 0 divided by anything is 0. Okay? 2 over square root of 1 plus n. Okay. Now, the left-hand side is always 0. How about the right-hand side? Okay, so the limit n goes infinity 2 over square root of 1 plus n. You can see we have constant over something going to infinity. So the answer is, yes, 0. Okay, so we have the left bound is 0. The right bound has the limit 0. That forced by squeeze theorem. Okay, the limit of the middle guy is also 0. Okay, and that's good because now okay, it's so sensitive to my fingers. Where are you? Okay, so we have the sequence also converges. All right, next, part F. Okay, we have n minus square root of n. Okay, so I want to recall. Okay, so what are the things we can tell? Okay, so let's make a list here. How about let's use green? Okay, so what are the things we can tell? Infinity plus infinity, can you tell what that is? Yes, infinity. Infinity times infinity, can you tell what that is? Well, that's infinity, right? And how about infinity minus infinity? Can we tell what that is? No. How about infinity over infinity? Can we tell what that is? No. Like 0 over 0, can we tell what that is? No. 0 times infinity, can we tell what that is? No. 1 over infinity, can we tell what that is? Yes, that's 0. 1 over minus infinity, can we tell what that is? Yes, 0. 1 over 0 plus, so what is 0 plus? That is a number that's getting close to 0 from the right. So it's a positive number, but it's smaller, 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 getting close to 0. So the answer is positive infinity. 1 over 0 minus, so it's a negative number, but smaller, 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 closer to 0. So that is minus infinity. Okay, so that's why the top line we can determine, the second line we cannot determine. So they're called indeterminate form. Okay. All right, so we have more indeterminate form. We have 0 to the 0, 1 to the infinity, and infinity to the 0. Okay, so those are all the indeterminate form. So in this case, n minus square root n, we cannot tell because it's infinity minus infinity. Well, however, we can, we're solving the problem, let's use black color. However, because we can change the formula a little bit so that we can tell. So can you see there is a common factor? You can consider n to be square root of n times square root of n. Then now you can see the common factor square root of n. What's left? Square root of n minus 1. Well, now, when n goes to infinity, you get infinity times infinity. So can you tell what is infinity times infinity? Yes, that is infinity. So we can tell now. Okay? So that's why the sequence diverges. Okay? All right. Next. Okay, so part G, this is actually the a hard problem of L'Hopital's rule. Okay, so let's plug in when n. Let's see what happens when n goes to infinity. Okay, so inside the parentheses, you can see that when n goes to infinity, we look at the dominant term. The dominant term is n and n. So the inside looks like 1. It goes to 1, right? And then here we have the n goes to infinity. So this guy is like 1 to the infinity. 1 to the infinity is actually indeterminate form. Okay? So when we see those type 1 to the infinity, 0 to the 0, infinity to the 0, we use L'Hopital's rule. Okay? How it works is first, we apply natural log on both sides. Okay, so ln of a sub n is ln of n plus 5 over n plus 1 to the n. Okay, why do we want to apply natural log? Because we can then bring the power down in front. So we have n ln of n plus 5 over n plus 1. Okay. And next, we can compute the limit now, right? So, compute the limits, n goes to infinity, ln of a sub n is the limit, n times ln of n plus 5 over n plus 1. Okay, let me make it bigger. Okay, so what is that? Well, you can see when n goes to infinity, this is like 0. This is like ln of 1, right? What's ln? Sorry, when n goes to infinity, n goes to infinity. ln of 1 goes to 0. So infinity times 0 is indeterminate form, okay? In order to use L'Hopital's rule, okay, so if you have the case of infinity times 0, you want to move one of the factor in the denominator so that you have infinity over infinity or 0 over 0. So in this case, which one do we move? Well, do we move the big guy, natural log, or we move the small guy, n? Maybe it's easier to move the n, right? When we move natural log, it's so complicated. Okay, so natural log, okay, you stay here, don't move. And then, n, when we move downstairs, do we just get n? No, you cannot just move the n downstairs. You also need to flip it. Okay, so move it downstairs and flip it. So the guy is like this. You flip it over. Oh, that's like that. Oh, that's weird. Okay. All right. Okay, so let's continue. Now, when n goes to infinity, we actually get 0 over 0. Yay! Then we can apply L'Hopital's rule. What's L'Hopital's rule? Okay, so L'Hopital's rule, that's the limits n goes to infinity of the derivative of the numerator over the derivative of the denominator. Okay, but here I want to do one thing. I know I'm gonna take the derivative of natural log, but you see, we're gonna use chain rule, and wow, for the u prime there's like a quotient, so I don't want to do quotient rule. So there's one thing to avoid that, is to recognize this giant guy to be ln of n plus 5 minus ln of n plus 1. So this is the property of natural log. Okay, so when we do this, it helps us to avoid the quotient rule. Okay, all right, so what's the derivative of ln of n plus 5? Well, that's chain rule, right? Where the u is n plus 5. So derivative of ln of u is 1 over u times u prime, but u prime is 1, minus so we have another chain rule where the u is n plus 1. So derivative of ln of u is 1 over u times u prime, but u prime is 1. How about the denominator? Okay, derivative of 1 over n. Is that 1 over n squared, something like that? Yep, actually, so this is like n to the minus 1. Okay, how do you differentiate it? Well, you put the exponent down in front, and then what do? You subtract 1 from the exponents, so actually you get minus 1 over n squared. Okay, what is that? Oh, I don't know what is that, so let's simplify it. I don't want to see fraction in a fraction, so let's simplify it. We combine the top together. So this is the common denominator, and then what do we get? What do we put on top here? Okay, so how do we get the common denominator? The first term we multiply by n plus 1. And the second term we multiply by n plus 5. And please, please here, don't forget your baby. Your baby is super important. Without your baby, you'll be wrong. Okay, oops, so let's continue. Minus 1 over n squared. Almost there. Okay, so this might be the hardest problems in this session. Okay. The top, you can see when we break the parentheses and then cancel, we have 1 minus 5. That is negative 4. And then we have n plus 5, n plus 1. And then we have minus 1 over n squared. Okay? Oh, this is too long. Let's make it shorter so we have enough space. Okay, what is that? Well, do you remember that a over b over c over d is a over b times d over c? So a is like minus 4, stay on top. The b, stay downstairs. The c is like minus 1, you put it in the bottom. And d is like n squared, we put it on the top. So minus cancel, right? And then, so we get 4n squared over n plus 5 and n plus 1. Wow, what is the dominant term of the numerator? Dominant term of the numerator is 4n squared. How about dominant term of denominator? Is it n? No, it's n times n, which is n squared. So that's why this guy equals to the limit 4n squared over n squared. The answer is 4. You see, the answer is 4. Okay. What's next? Okay. So, what do we start with? Okay, we start with ln of a sub n, right? So, now what is a sub n? Oops. Okay, so what is a sub n? Okay. Let me see. Alright, so a sub n is like a limit e to the ln of a sub n, right? E and natural log, they cancel, we just get a sub n. Okay, but now, what is the limit of ln of a sub n? The limit of, let me use different color. Okay, alright, we cannot choose it. It's okay. The limit of a sub n is 4. So that is why here we have e to the 4. Okay, let me fix that. Alright, so we have limits of ln of a sub n that equals to 4. So that's why e to the ln of a sub n is like e to the 4. So e to the 4 is actually our final answer. Okay, so this is quite a long step. That's why I said this problem is the hardest type of this session. So what is the first step? The first step is apply natural log on both sides and bring the power down in front. The second step, you compute the limit. Okay, you compute the limits, and then you're gonna create a quotient term so that it's like either 0 over 0 or infinity over infinity. Okay, and then you can use L'Hopital's rule and take the derivative of the top divided by the derivative of the bottom. So here, be careful. We're not doing quotient rule. So here, we are not doing quotient rule. Okay, remember what's quotient rule? Is the numerator prime times denominator minus numerator times denominator prime over the denominator square. So here we're not doing quotient rule. We're just doing the derivative of the numerator over the derivative of the denominator. So be careful with that. Some students make this mistake in Calculus 1. Okay, and then we simplify it until we get the final answer. So the last step, okay, the limit of a sub n is e to the whatever answer we get from the last step. Okay, so we have 4 steps for this problem. Okay, next, how about h? Okay, so h, when n goes to infinity, what happened? You can see that the inside the parentheses, we have n is the dominant term, 3n is the dominant term. So inside is getting close to 1/3, okay? And when n goes to infinity, what happened? It's like 1/3 to the infinity. Do you know what that is? Well, let me review with you. So you know a to the x, if a is greater than 1, we're gonna get increasing function, right? Okay, how about a to the x when a is between 0 and 1? We actually get a decreasing function. So 1/3 is between 0 and 1. We actually get a decreasing function. So, okay, sorry. Alright, so that's why we have the second picture. When n goes to infinity, this guy actually goes to 0. So that's why we get limit n goes to infinity of a sub n is 0. Okay, so in our last example, I forgot to say, because the limit is a number, we have the sequence converges. Okay, and then in part h, we also get the number 0, so the sequence also converges. Okay, let me put a line between between G and H, so you can see which one is okay. Alright, let's put a line here. Alright, let's continue. Okay, so let's work on this problem. Okay, so when n goes to infinity, ln of 5n squared plus 1 goes to infinity, so we have infinity minus infinity. Can we tell what that is? No. So let's express this in terms of other formats, okay? Other formula. So actually, what is the property of natural log? Okay, so ln of that minus that is the same as ln of 5n squared plus 1 divided by 3n squared plus 2. So here we are able to tell what it is. Okay, look at inside the parentheses, what is the dominant term? 5n squared over 3n squared. So inside, when n goes to infinity, we have 5 over 3 equals 2, right? So that is why. And then our limits will be ln of 5 over 3. And because it's a number, we say the sequence converges. Okay, that is part I. Okay, so let's talk about the growth rates of sequence. The following sequence are ordered according to increasing growth rates as n goes to infinity. Okay, if a sub n appears before, let me see. Yeah, before b sub n in the list, then limits of a sub n over b sub n is 0. Why? Because if a sub n, the numerator is smaller. Okay, if it's smaller, the denominator is bigger, then the quotient is gonna be 0. Okay, for the limit. All right, let's look at the list. This is actually quite a long list. Okay, but actually, let me simplify the list a little bit. Okay, so let's look at the simplified version. It actually tells us that the logarithmic function is the slowest. And then next, we have the power function. And then next, we have the exponential function. And then next, we have the n factorial. And then the fastest is n to the n. So imagine there are 5 guys, they're in a race. Who is the first place? The first place is n to the n. Second place, n factorial. Third place, b to the n. And then the fourth one is n to the p, and then the last one is ln of n. Okay, so how do I remember this? Well, let me just imagine an example. Then you can figure that out. Okay, let's say let n be 3. Okay, if n is 3, then ln of 3. And then this is like 3. Let's say 3 to the okay, let's say I remember. Okay, sorry. Do you remember we already figured out this guy? Okay, so in the first example of this video, we talk about exponential function grow faster than the polynomial, and polynomial grow faster than the logarithmic function. So actually this is true not only for polynomial, it's actually true for all the power function. So the power function could be like a 3/2 or 7/3, something like that. Any power. Okay, so now let's talk about okay, let's talk about this guy. Why this guy is true. Well, think about it. Now we let b be 3 and let n be 10. Okay, let b be 3 and be 10. What happened? Well, the first one becomes 3 to the 10. The second one is what? 10 factorial. And then the last one is 10 to the 10. Remember, n goes to infinity, so you can think about n is really a big number. It could be so big. Okay, so 3 to the 10 is actually 3 times 3 times 3. How many copies of 3 multiplied together? Yes, 10 copies. Okay, and what's 10 factorial? Well, that's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, and then the last one is 10 times 10. How many 10s multiplied together? 10 copies of that. Okay, so you can see. Well, of course, 10 copies of 10 multiplied together is bigger than the 10 factorial, right? And then compare the 10 copies of 3 multiplied together. Well, there's only like 2 number on the factorial, like 2 and 3 that are smaller than the 3's, but all the other factors are bigger than that. So that's why the total is the 10 factorial is bigger than the 3 to the 10th. So now you can see actually when n goes to infinity, n to the n is much bigger than n factorial and much bigger than b to the n. So that's why we have this list. So you don't need to remember this long list. Just remember this one, the simple version with 5 of them. Okay? All right, so that is sessions 8.1 and 8.2. Okay? Have a good day. Bye.